sharing this session. And this is the first hands-on session, so we will get our hands into the code. And so some brief things to be said before starting is that now in the website of the school, that is www.ssscha.eu, and then you can find the website from the of the school from there. And now there is an updated version of the PDF of all the tutorials, which have been updated. We fixed some errors, some small things that were missing since the version that we sent you 1 week ago. So if you can connect to the website and download the latest one, would be nice. And I hope all of you, most all of you, have the code working either with a virtual machine or with your computer. In any case, most of the organizers and developers are in this room, so we will go a bit around and help people to get started with the code. And so if you have problem with running the code, let us know as soon as possible so that we can fix it before actually going deep into the first hands-on session. Anyway, so the first hands-on session will be held by Diego Martinez, and it's going to be about your first SHA minimization, and I hope you will enjoy it. So let's start.
Okay. As the calculation is going to take a bit longer in some laptops, I will prefer to make first put your calculation running, and while it's running, I will explain the code for you. Maybe that's better. So there is a directory. Quantum dispersion. Okay. So. Okay. So we're going to go into the directory called 01 first SHA simulations, if you will. And there is the first calculation that is with this SHA slash or sub aurum. This is quite small here in the graphic. So you can put it as Python 3 or Python SHA out.py to run it. And if everything is okay, a lot of things are going to happen in the screen, unless you redirect the output to a file. But first, in this calculation, we're going to look how it looks the calculation, so it's not strictly necessary to redirect it to a file. So if we put in something like this, and meanwhile it's calculating, I'm going to explain a little bit about the code. So, okay, it's going. This is more or less the code. It's very small here. Maybe I can change the size of the size of the screen size. I don't know here how it's done.
Control plus.
No problem. This here configuration and preferences, so it should be font and colors. And font. And I can put it bigger. So probably like this. Okay, so here you can see it better. So this is a basic code for calculating a first free energy minimization. And for that, the first part is just loading the libraries for the Python code that are the SHA libraries, the set constructor, the ASE for the calculator. This and the typical NumPy, matplotlib, and the operating system. The first thing that we are going to do is some preparatives for the calculation. And for that, we are going to load from a crystallographic file as SSCHA, crystallizing input file. This is just the preparative for this case. You can use this kind of file. You can, in fact, use any kind of input file supported by SAE. So you can construct your own things, and if you not, there is also the open bubble and that kind of program that can change from one format to another. So there's no problem in that respect. So here, first we set the calculator from the SAE, set the relax for the goal structure, loading the structure and the calculator. And this is for calculating the harmonic dynamical matrix, the harmonic phonons. We do it with this here, this object. And from that, we obtain the dynamical matrix that we can have symmetrized and save in a file. This is just the preparatives for obtaining we are still didn't make any SHA calculation. SHA calculation begins next, where we first make positive definite if we want. Well, this was important for the whole calculation. We set several parameters. We create the ensemble of random configurations with the temperature, set the object of the minimization with the sample, set the minimization step, and relax. And with that, this is EO info for having an output. For that, we can get the dynamical matrix of the relaxed with the SHA code. We can see more or less the parts of what we are doing here with this graphic here, in which first we load the structure and the calculator, that we load the relax, and for that we use finite differences to calculate the dynamical matrix for the harmonic system. This is just the preliminaries. For the SHA calculation, is the second part here, where we load the dynamical matrix and the calculator. We use the dynamical matrix to calculate an ensemble of random configurations. From that, we include in the minimized object. This minimized object can do one-step minimization, and so you can have very control of these kind of things. But we can also use this object, the relaxed object, that automatizes the SHA calculation. Now let's take a look at what has our program been doing here. We can see here, we're going to freeze one of these things. I think that I can freeze. Okay, for example, this one here. This is the output on your screen, in which you have the step. Okay. Here, the step in which we are in this moment is the 39. This is the length of the step. In this case, it's good, and try to make a little bigger for a steeper distance. The number of symmetries, the free energy from the harmonic contribution. Here you have the energies, the gradient, the modulus, the conjugate effective sample. This is how good the Gaussian is to fit to our calculation. You remember from the John speech, we fit the the wave function to a Gaussian, and this conview is setting how good is that fit of the Gaussian. And from that, let's go into the several things about the gradient and saving the data in these files, minim info, that we are going to see once.
Excuse me?
Yes?
Just going back to this conmu effective sample size, what does this number mean? Is it 23% or is it the reference?
What is the reference? It takes the number of configurations and makes the ratio with the ones that are fitted. So if we have, in this case, it's 0.5, so if half of the configurations are outside of this gradient fitting, then we have to recalculate the configurations again.
Also, it's not look at the number of samples that
Yes.
fit well.
Yes.
Actually, you can see there that
Yes. In this
case, so that point, the ratio is chosen 0.5. You have in that conlu is 23 point whatever.
we have 50, so 25 is the number that if this goes to that number, then it's wrong. It needs to calculate a new configuration, a new set of states for the configuration. New configuration.
So that's why it's put here that if this becomes less than 0.5, the ratio, you can see there. So therefore it tells you, according to your input criteria, you are out of the statistical sampling. So that's why at this moment, it stops one minimization in a set of configurations and it will recalculate later. Clear?
Yeah.
That's the point.
So let's see what is the calculation. So basically it's doing that. We're now for the step 75, and this will take 5 minutes or so.
Are you all running the calculation somehow or?
Yes.
Yeah, it's running? So
I have a problem because I have installed the program in our workstation. So it seems that something needs to be better in your laptop.
Something to restart?
Yeah, no, I haven't installed the electricity. So maybe it's check it. It seems that some problem with back, some activation, something.
You, how did you install in the cluster?
Yeah,
Ah, you have it. So you follow the instructions. Okay.
running this test, so something, and you will be okay. But now I'm trying to run this
Yes.
one, because we have this version of Python,
Yes.
and
That's
yeah.
Let me try one thing. Instead of putting this, that's what it is. So what
I don't know. So here in the input, one thing that is common is that it was chosen to create 50 configurations per each population. This is the word that I was using, of per ensemble. Okay, and I think there was like a parameter how many ensembles you are going to calculate maximum, and I think it was 20.
20.
Okay, basically these were all the input parameters that you were using. So I think it will maximum. If it doesn't find the minimum, it will continue doing calculating ensembles until a maximum of 20 was the
20,
maximum,
yes.
right? So you can control how many populations or ensembles it will.
How many tries? Yes.
Maybe I can.
How much ensembles should use?
maximum number of ensembles.
Ah,
Have you used those?
that depends on the problem.
Depends on how far from the minima you start. Right. That depends on the problem. Sometimes with one is enough. Sometimes we need hundreds. So this depends how far you are from the minima. Like it can be around less than 10 easily. Yeah, you can be less than 10. Yes, I know, but can be some cases. Okay, I want to relax it from a random.
Yes, on a random, you need more number of tries.
I don't know if any of us have do material analysis. No, because you first relax with your feet and then you.
We usually start from a harmonic solution
Yeah, you first minimize
or a previous calculation from SHA. So you need first a starting point. Random then means that you have to do more cycles.
Random dynamic matrix. There is a random atomic position harmonic structure, harmonic dynamic matrix, or random structure. Yeah.
Yes.
I would say that most times you want to address that problem, you first minimize the TFT to the one of the higher minima, and then from there you somehow are like a more meticulous and you don't minimize the actual free energy. But you could, from principle, minimize the free energy from the start. But I don't know how many.
Porque esto es distinto.
Yeah, I would say like you can work in a
que se intenta crear una nueva configuración. Esto va haciendo el cálculo SAT utilizando la misma gaussiana tanto así como puede, hasta que se sale de la número. Entonces dice que ya no es válido, entonces ya otra nueva configuración. Y eso hace siempre 50 configuraciones. Es el número máximo de nuevas creaciones de la gaussiana.
In the context of translation, from my assignment you use will generate a lot of random.
Cada una tiene 50 configuraciones. Efectivamente. Aunque creo que lo está tomando en forma grupal, así que hace la gaussiana, crea las configuraciones, crea un programa gaussiano y a partir de ahí va calculando el dispersion system hacia so it's doing the dispersion system and going using the same configuration until that configuration goes outside of the Gaussian. And then it creates a new configuration and up to, in this case, 20. That's a limit for this automatic thing. Because you cannot just do it manually. You can do it manually. In that case, you can set manually with step, with the deletion, how. So you can do it with everything manually. But right now we are doing it with this collapse that automatization of these things.
Yeah, when you minimize the setting of I don't know what you use the previous generated version to make your second trial. I don't know about that. So I don't know how to yeah, from P1 from also I think it's what people are, I'm not aware of anyone using theory. In principle, I don't know. Solving meaningful factor. Meaningful factor. Meaningful factor. Meaningful factor. Meaningful factor. Yes. Yeah. So it's normal. Yeah. Why? Because it's random. Pero
ya finish here. ¿Puedes tirarlo sin más? O
Bueno,
voy a controlar esto y dispositivos, redes compartidas y eliminar la que tengo aquí. Y vuelvo a poner la pantalla completa. Ya puedes enchufar aquí.
This will be shown by
That's why it's not so important how is your calculation? Have you finished? Yes. Okay. So for the people who are still calculating, you can make the calculations later or something like that. Right now, the important thing is in this case the calculator is finished, and we can now see the output. For that, you can see here that we have a kind of number of new files, including the harmonic the dynamical matrix here, that are divided in different files with but the important thing is here in minim info point dat and the minim info point frex, with the frequencies and this kind of data. You can see these files, well, you can use Beam to just take a look at these files, but you are going to look at a lot of bunch of numbers. So what the important interesting thing okay. Is that you can visualize the data with, it was, I have to check the name of the command because I don't remember right now. It's Okay, it's quite simple. Just with SHA. Yes. SHA plot diagram. And with this, you put the name of the output, in this case, is meaning info. With that, we got this output. That. Let me put the pointer somewhere. I have it here in my. The command line, yes, is here. SHA, no, SSCHA, yes, plot, minus plot. Okay. And while in the previous class, you see this graphic here presented by Jan with the free energy as we have calculated, the consume sample, the force energy, the structure gradient, in this case the gradient will move. So this case we made 1, 2, 3 configurations. So in 2 occasions, the Gaussian, starting Gaussian was not good enough at some point, this point here, and calculate a new one. The gradient, well, the structure didn't change, it's always 0 in this case, because this is a gold crystal. The force constant, you can see here that goes down, and the other figure here is the evolution of the auxiliary frequencies, going from the harmonic to the SHA anharmonic. As always, we have to remember that this is not the true frequencies. This is the working frequencies. Later, in some later examples and theory, we will see how to obtain the true frequencies, the true anharmonic frequencies. And this is it, except that we can also plot more data. In this case, we can, you have here a file called plot dispersion that we can take a look. Open plot dispersion. This code here, this is just takes the output of the data and plot the power spectra or the states in a way. I don't know if I will have to explain this because it's mostly matplotlib with numpy, with just the constructor for loading the system, in which this is just setting the special points here. This is the output, loading the harmonic and the SHA calculated dynamical matrix. This is the number of irreducible Q points. This is the same as the number of files that we have here this harmonic being with a number. And then we have a script that just load this matrix, get the path integral, and plot the data. So it's nothing special, and in that sense, we can run that with the Python. And that way, we obtain this graphic here with the power spectra of this calculation, in which we can see here in dot the original harmonic and in red the SHA approximation, the SHA calculation.
Yeah.
Okay. So let's pass to another calculation. If you have finished with
So
this,
is there any question at this level, or how is it going? Maybe it's a good time to stop. So you understand that the calculator here is an empirical potential, which it's this EMP, which is a bit whatever. It's very bad probably, but it's something fast to do it, right?
yes, usually you should do the calculation with an arithmetic or whatever you want.
So also note that you have the free energy in the end of the calculation. You have the free energy. So basically, remember, this is what we are doing. Basically, minimize the free energy. So you have that's the solution basically. And also here, remember we are talking about the centroid position, right? So what is this output written, right? So maybe this is within the Python structure. It knows. So eventually you could print with this is a Python, so it's very modular. So you can work within the same script. You can do whatever you want, right? Within Python.
Yes, that's the good thing about Python. Once you have this calculation, you can work with the data and take to another codes, mix it with another kind of libraries and that kind of thing.
But if you go to the output dynamical matrices, which are written in quantum espresso format, okay, these are the final auxiliary dynamical matrices. There, in the header, you have the structure written like in the quantum espresso form. So this is, let's say, the final centroid positions of the minimization. There you go, there, right? So you have. So there is the quantum espresso dynamical matrix file that you get in the output, and then you have the final basis vectors and the positions of the atoms, which in this case is all in FCC or BCC.
Yeah.
So I mean, so you have that there. But this is where you have your final information on the centroids, right?
So we can see the frequency are hardened after doing this kind of thing. And how can we judge like this hardened frequency is right or not?
Whether it is,
I mean, the frequency are hardened, like the incorrect. And how can we judge like this frequency are correct?
are right,
Are correct?
are correct.
Yeah.
So
I mean, because we introduce unharmonic and the temperature, and the harmonic frequency will be hardened or incorrect. And how can we judge this calculation or the frequency gets the convergence? So maybe in this case we are using a value of the meaningful factor, which is quite large. So the delta that we was introducing is by default at 0.1, another 1. So it's you are stopping where the gradient is very huge. So if you reduce that value and you can modify the speed and modify the value of meaningful factor, then probably to a much smaller value, then you will see the frequency switch as well. So like it was
factor, which is this variable which determines how small the gradient is when to stop the calculation, then you can really see the gradient go down to 0, and then you will see the frequency go into account. And that's all. So,
Of course, not saying the frequency between the harmonic and R is quite large.
Yeah.
This is why we sort of how can we make sure our calculated frequency or the only band is correct.
So if the gradient is close to 0, this is correct within the method, then in this case, this is not a good frequency because the potential is critical potential, and it's not very good potential for gold. It's not very accurate, let's say, to do accurate calculation, but still, it's significant to the calculation.
And we just see this figure and the frequency just increase, and we can see the harmonic is strong or is strong, or we can use this figure to chart like that.
Yeah, it's even more this one. Like that, they are the same. Yeah. So the figures you see here are exactly the same here. Here they are not divided by 2 points. Here they are not divided by 2 points. So they are the same. So you can see they are the same.
Like the low temperature or the high temperature.
This really depends on the system. There are systems in which frequency can change by a lot. So for example, the Palladium hybrid was shown before, it was changed by 5 times. So sometimes it's depends on how and how. And these are close to the system. So this is very actually the minimization that you have. So if you look at the energy decreasing, it's not. It's like the energy of the system cycle.
So it's something that
Which
recent months has made an
because
update
actually
on the library.
we
It seems something of this,
it is equivalent
some
to
of
the
these errors can
so we are
come
actually
to
solving our minimization. But this is equivalent to solving the system. There are two phases of the string. In our case, we are actually minimization. But it's equivalent of solving the system.
This is
No, this is not. No, this is actually
this is not the position where it's not? Yes, yes. So, no, we don't know yet what so,
So what is doing the potential the answer now is this effective potential for gold, which is the atomic potential divided by the package
of the output. So no, it's not the concentrated calculation.
Hands-on-session, we will use actually one express.
Okay, don't understand this. Correct. No,
So this can be
a 444 supercell that was determining the input. I don't know if you realize. Okay? So in principle, in the output you have how many? 13 dynamical matrices. So why 13? In principle you have 4 times 4 times 4 supercell has 64 commensurate Q points in the relevant zone, but by symmetry, many of them are equivalent, so therefore we just print, so the SSCHA code just prints those that are symmetry, the irreducible relevant zone. Okay? So that's why it's like in quantum espresso, if you calculate the phonons as well, it only prints the Q points in the irreducible relevant zone. Okay, so this is the same. Okay, that's why you have here 13 dynamical matrices in the output.
What's the depth on the end of such a relaxation? It's not the frequency. This Hands-on-session. It's not physical.
It's not physical. That's another question also asked me there. So and Leo has plotted some frequencies, some phonon spectra. You can plot it there. These are the phonon spectra that come from the auxiliary points. Okay, so you can define that, right? So this is free, but remember, these are the point of the today morning's lecture was that actually these are auxiliary phonon frequencies. Okay, so tomorrow you will see what are the physical, right? But still you can plot them. Why not? You're free to plot, right? But it's good that you know what you're plotting, right? So these are the auxiliary phonon, which are different from the harmonic in the solution, right?
Maybe this question will be covered in another direction. Okay, but I can see what sometimes it is possible that auxiliary frequencies become imaginary.
No, the auxiliary dynamical matrices never become imaginary.
Never.
No, because maybe this I didn't stress in my lecture enough. So because they are describing a wave function, so this wave function needs to have a width, right?
But by some technical.
It's true that maybe with some, if the step is too big, and sometimes the code would crash.
That's why you have the false positive part in the code. Because in case you start with ones that are negative, if you start with the harmonic approximation, you may have some that are negative, you force them to be positive.
At initial step, but when some possible, when it relaxing, we can.
So in principle, the system is really unstable. It should converge to a very, very flat wave function, which basically really has for the auxiliary frequency. It is true that this is difficult. So if the step is a bit too large, so in the conjugate gradient, it might go to imaginary. It doesn't happen very often, but it can happen. So if that happens, you need to reduce the step of the step in the conjugate gradient. You need to reduce it. And in principle, the code should converge to a value which is with an auxiliary frequency that is very close to zero. Exactly. Instead of using the preconditioning, there is another way. So instead of using preconditioning, it's the way of minimize, not with respect to not calculate the gradient, with respect to the force function matrix, but with the fourth root of the force function matrix. And in this way, you can guarantee that you will make this in a.
That's my question. Representation. Unnecessary, or it is well.
It is unnecessary. It is both unnecessary and very bad because indeed then you will need, and we don't know the analytical equation because you will need to calculate the second derivative of the primitive with respect to the fourth order root of the, and we don't know the analytical formula. So that would be a mess. So actually, I think the code crashes. If you do that, really. Okay, so but no, if you are using preconditioning, don't use the fourth root. If you are using the fourth root, don't use preconditioning. Use let's say the rule of thumb. Claro, esto es aleatorio. El punto de partida no es el mismo que. Claro, o sea, esto es aleatorio. O sea, si con el número de configuraciones fuese infinito, ya sería difícil resultados. Pero como está centrado en 50, o sea, tenemos un error estadístico. Entonces, no todas las conversiones van a ser igual. Está el mínimo de los errores que están en perfecto. Es porque claro,
So it doesn't matter.
yeah, probably we need to use a bit a meaningful factor, which is maybe it's not written there, but there is another flag, which is remember I had a delta. That it was like the value of the gradient with respect to the value of the error. Right? So we didn't go to such a small gradients. 0.01. So if you put 0.00001, right, I think it's very smaller the value, and therefore the gradient will go really to zero, and then the yeah, sure, but it's as well. So I think even in the screen that we use it, in the script that you run, yeah, that one. This one. No, this one. So you need to. I think it's a quite meaningful value. So you need to put SHA. Meaningful factor and there is no value. Before you start relaxing.
You can put it as a variable inside the minimizer.
So when you put minim
No, minimizer, ensemble, minimum, minimum factor.
so where do you put the meaningful factor?
In the, so you can put it in various places. One, then when you define the minimizer, you have somewhere minimizer, la variable que le hace el ensemble.
Sí, pero so one question that is appearing is that maybe you have done the minimization and it's not the same as the one provided in the PDF. So this is why is that because each of you generated different random configurations. So therefore the result is not going to be the same because it has some stochastic noise. So you have just 50 configurations. Eventually, if you increase more the number of configurations, it will become closer, so you will suppress the error, and this will, in this way, the result will be better. Okay? Another question that we are getting is that the frequencies did not really flatten, as I showed in the example. Okay? So this is because the delta that I introduced in my lecture here by default is 0.1, which is a rather big value. So you can reduce that by using a flag which is called meaningful factor. So which is a variable, you can say where it is, where you put the meaningful factor.
Minimize and relax. The object of the calculation. One of the
Claro, pero no está, no se minimize.
Okay, shall we move forward maybe with something more a bit, maybe?
I think. Okay, let's continue with another calculation. So right now we calculate a simple calculation. Where is this now? Okay. DE. I have to remember which file I have to look now. Here, thermal expansion. Open thermal expansion. So now, this one here is another calculation. In this case, we are going to show how to calculate for different temperatures. In this case, it's the same, using the same calculator. Now we have a range of temperatures. We're going to, because we don't have much time, we're going to change the step of the temperatures to a bigger number. And the difference here is that we have a loop here that starts here in this while to calculate for different temperatures. And I think this is the other thing that I have here, because no, we have also the different, instead of calculating with a fixed cell, we're going to use this BC relax that calculates for a variable cell and a target pressure of 0. Yes. For just to remember that if you're going to do the calculation, I just added here to 150 for the step of the temperature to make faster calculation. So right now we come here and do the same Python and the file with thermal expansion. And the output should be something very similar, not the same. Calculate the configurations.
So the difference now is that the temperature is changing. So we are doing a two-point loop on temperature, different temperatures. But the structure is relaxed. So the cell is relaxed.
The cell, we are going to change the cell.
So that it's pressure 0. So this means that you are actually calculating thermal expansion. Yeah, the temperature is accounted in our distribution function. It depends on temperature. So here temperature in the Gaussians that I was describing there, the width is temperature dependent. So therefore, temperature is there. Likewise.
Exactly like in the last so you do the VC last at high temperature, pressure is at 0, you get the noise.
And still, I don't think that
So in states, have a look at this.
it's basically repeating the same calculation for different temperatures in cycle. So it's the same previously, but now we're doing for different temperatures with changing the cell to keep the pressure at 0. That's why we use the thermal expansion of the
It starts at 300, the steps of and then this is the loop, while B is smaller than the last one, it is adding the P plus adding potential. So zero plugin is well defined. There's absolutely no problem. As I said, so we will include quantum fluctuations, there is no problem. So the temperature is not an issue.
So let's say it's dynamically stable. So physically exists, it cannot be. Right?
Sure, because you can't have it, because you have binary economic system, it's not defined. That's perfect. Yes, yeah, we think the approximation of the self-consistent function. Yes. So you can do it. So yes, then so we will give you a free energy value. Only the one thing that I'm going to get now is the technical song. Okay? But it will give you a free energy value. But probably this structure is not the free energy value. It's probably not the free energy value. So then, and this is what you use in that you should calculate the free energy equation. The free energy equation will tell you whether this is precisely by symmetry maybe you cannot go right? But it will tell you, oh, you have here so this means that the system will want to relax. Then, well, then you know that this is not a structure that has to go to. So therefore, you can do it. But it's not a structure that goes to energy. So then you are not with the right structure. No? So you know that it's not a structure, you know, nothing can be. It is that.
So you will define your knowledge process.
Right, but these calculations are not
So we need just to create
not so easy to get real energies, not so easy to get phonons, or life cycle phonons, display different kinds of people,
because we can also calculate with another calculator, for example with the quantum espresso. So meanwhile this is running, we can show the code for, in fact I can show the results for this calculation here, but I think you don't need it. This other code here, it's for calculating with, instead of this EMT calculator, for the quantum espresso. And for that, we define the typical things for the quantum espresso. They could draw these things that are typical for quantum espresso. And then later, the pseudopotential here, setting the command that were used for the quantum espresso. So we change the calculator with the one of the espresso. So it's just that you call the espresso that is defined from the here from ACE. Where is the espresso? Millimeter, shout it, import the constructor from calculators here, from here, from ACE calculator espresso, import espresso. So here is we import the espresso from ASE, and later, following the construction of the SE formalism, input the data and set the calculator with espresso. And the rest is the same. The rest is just the same. Just changing the calculator for any other calculator. In this case, it's the quantum espresso. You can use any calculator that is supported you have to have that calculator in ASE. Then it works. It's just using ASE to get the force and energies. And when you have the force and energies, it calls into the SSCHA code and it runs. So, yes. Change the code to run. These calculations that we are doing now of the temperature, I have the results. Just to show. Just to show what's the end result of this calculation of the thermal expansion with N to B, in this case, with only 5 points, because we remember that we changed the step of the temperature. That is different than the one provided in the documentation, have more points. And here, yes, this is where you see the change. More points when you have is a better.
We have the structure
It's in the open data. Yes, because at this temperature, it has an output of the here. You have an output here of the different temperatures. Where is here? You see here SHA, the dynamical matrix with T300 here. This is one of the outputs that we have. In this case for the 300 Kelvin. We have the rest should be over there. It's also and the output. Let me check it. Yes, we have here the output that we are putting into minim and the temperature. So in the directory where you're doing the calculation, you should have this minim T and the temperature that is calculating right now. So we should have minim somewhere. I don't see it here. Saving minim T. And relax set of functions minim output. And here I only see the one for 600. I don't see it here.
There are inside.
Ah, yeah. Yes, they're here. So here we can do the sharp plot data with this minim 300, and we still have here the one for this 300 the Kelvin. And later, as we make the different calculations, we should have the other ones. Yes, for example, here we have 40 different temperatures, and we can do that. T from 1 to no. And comma 450, comma 600, comma 5, 6. Ah, okay. So I have one. Because I probably then finish this calculation. Yeah, still making the calculation.
So it would be that order, right? So that you are using I also tend to like when the don't change anymore. It's like, no,
It's like contrasting. It's very that in reality yeah, because you don't know how you can can use for a scale. That's what I never. I only have time to use this for actually. You know, like the most expensive thing in the population.
So if you want to take some coffee, because the next part should be making finish this calculation and plotting the graphic for the temperatures. And that's I'll show you earlier how to do it. Next one should be make using the calculator for the quantum espresso. That is spent somewhere. We will do it later in the next one for the cluster, calculating the cluster. So we can stop now and take some coffee.
Okay, so I don't know, you got an idea of how these things run, right? With an empirical calculation.
And also, the last example is with quantum espresso locally, right?
Yes, okay.
Right? Is that how the things work? Okay, so maybe we can take a coffee break now and we come back in half an hour, or if you want to ask questions right now as well, you can take advantage.
Código lo dejo, ¿no?
Es cierto, es cierto. Ahora mismo está haciendo aquí cálculos, pero no tampoco es para ponerse a ello. Podemos parar el OV.
Sí, era más que nada por eso.
Sí, podemos detener la grabación.